Students, in last class we have discussed about the reactions of aldehydes and ketones with the derivatives of ammonia, that is NH2G. Okay, and in this class we are going to discuss about the iodoform test for aldehydes and ketones. Okay, and before going to discuss about this one, first we have to discuss about the haloform reactions. What? Haloform reactions. Then what are these haloform reactions? See, the process of forming the haloforms which are having the formula of CHX3 is called haloform reaction. Haloform reaction is the reaction which will produce the haloforms of the form CHX3. Okay, here this is the general formula. This X may be either Cl, Br or I. If it is an Cl, then it is a CHCl3, that is chloroform, and it is a colorless liquid. Okay, and if it is a Br, then it is CHBr3, that is bromoform. This is also colorless liquid. If it is iodine, then it is CHI3, that is iodoform, and it is an yellow colored precipitate. This iodoform is an yellow colored precipitate. Okay, these are haloforms, and the haloform reaction we can write like CH3 C double bond OH. This is what? Acetaldehyde. When it is treated with 3 moles of halogens in presence of 4 moles of sodium hydroxide, we will get CHX3. See, this alpha methyl group, that is the methyl group which is attached to the carbonyl carbon of this aldehyde, is converting into its haloform. Okay, and the rest of the part of this aldehyde will be converted into the sodium salt of the corresponding carboxylic acid, that is HCOO minus Na plus, and 3 moles of sodium halide plus 3 moles of water. Okay, this is called what? A haloform reaction. Here the formation of haloform is there, therefore it is called haloform reaction. Okay, like this we can write for ketones CH3 C double bond O CH3. This is acetone. When it is treated with 3 moles of halogen and 4 moles of sodium hydroxide, we will get this alpha methyl group as a haloform, and the remaining part of the ketone is converting into its corresponding salt of sodium CH3COO Na plus, CS3COO minus Na plus. Okay, and 3 moles of sodium halide plus 3 moles of water. Okay, these are called what? Haloform reactions. And why we are studying these haloform reactions here? See, these iodoforms are there, na? Particularly we are concentrating on the iodoform test only. Test is the test in which we can easily come to know about the type of an aldehyde or ketone which is present in the given sample. If the aldehyde on reaction with some amount of halogen with some amount of sodium hydroxide, that is 3 moles of halogen and 4 moles of sodium hydroxide, if it is giving an yellow PPT, then we can easily come to know that that aldehyde or ketone is having an alpha methyl group, that is alpha methyl group, or we can say it is having a group of this type. Okay, or we can say it is a property of the aldehydes or ketones which are having alpha methyl groups or this type of groups to undergo haloform reactions. But particularly in haloform reactions, these chloroforms and bromoforms are colorless liquids, and we will not get any color change during the reaction process, and hence we will not get idea about the formation of products by this type of haloforms. But particularly concerned with the iodoform, at the end of this reaction, haloform reaction, if we are getting yellow colored precipitate, then easily we can say the aldehyde or ketone which is under the examination is having an alpha methyl group, or this C double bond O CH3 group. Okay, these type of aldehydes or ketones can only give the iodoform test. The aldehydes only CH3 C double bond OH can only give. Okay, except this aldehyde, no one aldehyde can give the haloform test. Why? Because if we are changing this CH3, then we are losing our alpha methyl group. The presence of this alpha methyl group is must and should to show a haloform reaction. Therefore, only this aldehyde can give a haloform reaction. And coming to ketones, the ketones of the type R C double bond O CH3. These are called what? Alpha methyl ketones. Alpha methyl ketones can give haloform reactions. Okay, then coming to the particular explanation of this haloform test, we can write certain aldehydes and ketones having alpha methyl group. Certain aldehydes and ketones which are having alpha methyl group on treatment with I2 and NaOH gives yellow precipitate with antiseptic smell. This confirms the presence of alpha methyl group. Okay, take for example CH3 C double bond O H acetaldehyde. When it is treated with 3 moles of 4 moles of sodium hydroxide, 4 NaOH, we will get CHI3. It is an yellow precipitate. Okay, yellow precipitate, and this rest of the part is converting into its sodium salt of carboxylic acid plus 3 moles of sodium iodide plus 3 moles of water. Or we can take CH3 C double bond O CH3 acetone. Okay, when it is treated with 3 moles of iodine and 4 moles of sodium hydroxide, we will get CHI3, which is a yellow precipitate, plus CH3 COO minus Na plus 3 moles of sodium iodide plus 3 moles of water. Okay, these are the examples for the iodoform test for aldehydes and ketones which are having alpha methyl group. Okay, and here why we are not using the Cl2 and Br2 here? Because if they are using in the haloform reactions, we will get chloroforms and bromoforms respectively. Those chloroforms and bromoforms are colorless in nature. and those haloforms will not show any color change during the reaction, and therefore we cannot judge the change in the products to judge the type of an aldehyde or ketone which is present in a sample. Okay, that's why we are taking the iodoform test, the formation of an iodoform. Okay. Coming to the mechanism of this reaction, see here I am explaining the mechanism for acetaldehyde. Okay, CH, I will write like this: H C double bond O CH2 H, HC double bond O CH2H. This when treated with sodium hydroxide, this sodium hydroxide in aqueous state, it is there as Na plus and OH minus, and this OH minus will now act as a base, and it will drag the alpha hydrogens which are present on the alpha carbon. These hydrogens, alpha hydrogens, are highly acidic in nature, therefore they can easily go as H plus, and it will go out as OH as H2, and this bond will now move towards the carbon, and here we will get a H C double bond O CH2 minus. Okay, and this negative charge will now delocalize through the C double bond O, and here the oxygen will get a negative charge CH2, correct. And when it is treated with iodine, this iodine is there as a I minus I plus, and this negatively charged electron pair will now delocalize through this oxygen carbon single bond, and this double bond will now move towards a carbon, and the positive iodine will now combine with this negatively charged carbon to form HC double bond O CH2I. This negatively charged carbon will now attract this I plus positively charged iodine, and these bonded pairs of electrons will now move towards I minus. Okay, and this I minus and this Na plus, this I minus and this Na plus will go out as NaI. Okay, and this when treated with another molecule of sodium hydroxide, this OH will now drag another acidic proton and go out as water, and here we will get H C double bond O CHI minus. This negative charge will delocalize, and H C O minus and double bond CHI, correct. This when treated with another molecule of iodine like this only, the positively charged iodine will go with carbon by the delocalization of this negative charge, correct. And HC double bond O CHI2, and the negatively charged iodine will go with this sodium as NaI, correct. This here also I will write I minus I plus. This positively charged iodine will be attached to the negatively charged carbon, and the negatively charged iodine will combine with the Na plus and go out as sodium iodide. Okay, this when treated with another molecule of sodium hydroxide, this OH minus will now also act as a base to drag this acidic proton, and it will go out as H2O, HC double bond O Ci2 minus. This negative charge will also delocalize, and here we will get HCO minus O minus double bond Ci2. Okay, when this is treated with another molecule of I2 which is having I minus I plus, by the bond delocalization, this positive iodine, that is plus I, will combine with this carbon C double bond O Ci3, and this negatively charged iodine will combine with this Na plus and go out as NaI, sodium iodide. Okay, when this is treated with a last molecule, that is the fourth molecule of sodium hydroxide. See how many NaOH we are using here? 4. See, 1, 2, 3 and 4th one. And how many sodium iodides are liberating here? 3. See, 1, 2 and 3. How many H2O are liberating? 3. 1, 2 and 3. Okay, this is a fourth molecule of NaOH we are adding to this molecule. See here, instead of acting as a base, this hydroxyl group will now act as a nucleophile to attack on this carbonyl carbon. This OH will act as now nucleophile. Why? Because here there is no acidic protons on this aldehyde. Therefore, it will act as a nucleophile and attack on this carbon, and this double bond will now move towards the oxygen. The pi bond electrons will now move towards oxygen, and hence here we will get H C O minus H plus, sorry, Ci3, no, it is, sorry, Ci3 OH, correct? Then now this negative charge will delocalize and this Ci minus will go out of the mixture as a Ci minus, and here we can write H C double bond O O H, H C double bond O OH, and plus Ci3 minus, correct? And this Ci3 minus will now drag this acidic proton, and this bonded electrons will move towards this oxygen. Okay, that we can write as HC double bond O minus plus CHI3. This is our iodoform, CHI3, our iodoform. Okay, and this is where it is HCOO minus is there, na? Then now it will combine with this Na plus and forms sodium salt of the corresponding carboxylic acid. Okay, this is the reaction mechanism for iodoform test.